Hey, welcome. Today we're diving into one of the most important processes in all of chemistry. Seriously, this is the engine that powers everything from life itself to the phone in your hand. We're talking about the world of redox. All right, let's start with a little riddle. What could possibly connect the slow, silent creep of rust on a car, the sudden jolt of power from a battery, and the very breath you just took? They seem like they're from completely different worlds, right?
Well, there's the answer. Deep down, at the atomic level, all of these things are driven by the exact same elegant action, an electron hopping from one place to another. This is the great electron exchange.
And that transfer is what chemists call a redox reaction. Now, the key thing to get is that it's always a partnership. You can't have an electron just leave an atom without having somewhere to go. So one atom loses, another one gains. Always.
So, how on earth do you keep track of who's losing and who's gaining? Well, chemists have a classic trick for this. Just remember the phrase, oil rig. Oxidation is loss, reduction is gain. It's simple, it's memorable, and honestly, it's a lifesaver.
Okay, so if electrons are being traded back and forth, how do we actually keep score? How do we know who's up and who's down? For that, we use a really clever accounting system called oxidation numbers. The best way to think about an oxidation number is like an account balance for an atom's electrons. It's a hypothetical charge that tells us whether an atom is in an electron surplus or deficit within a compound. It's our tool for keeping the books. And like any good accounting system, there are a few ground rules. An element all by itself is at 0. Hydrogen is almost always a +1, and oxygen is usually a -2. Get these rules down and you're pretty much set for most situations.
All right, let's put these rules into practice. It's puzzle time. Let's take a look at this dichromate ion. Our job is to figure out the oxidation number of the chromium in there. So, take a second. How would you start?
Let's walk through it. First, we know the whole thing has to add up to -2. That's the ion's charge. Okay, next we look at what we know for sure. Oxygen. There are 7 of them, and each one is a -2. So that's a total of -14 from the oxygens. For the whole ion to be -2, the 2 chromiums together must be +12. And since there are 2 of them, each one has to be +6. Done.
Okay, so we can track the electrons. Now let's meet the key players in this drama, the chemical agents that are actually doing the electron donating and taking. Now this is where a lot of people get tripped up, so let's lock this down. You have an oxidizing agent and a reducing agent. The oxidizing agent is the one that causes oxidation by taking electrons from something else. So, because it gains electrons, the agent itself gets reduced. See the twist? The reducing agent does the opposite. It gives electrons away, causing something else to be reduced, and in the process, it gets oxidized. Let's meet a celebrity oxidizing agent, the permanganate ion. This thing is famous. It's an absolute electron thief. It loves to pull electrons away from other substances. And you always know when it's around because of its incredibly intense, vibrant purple color. And here's the really cool part. When permanganate does its job, when it grabs those electrons, it transforms. The purple permanganate ion becomes the manganese 2+ ion, which is totally colorless. This color change is like a big flashing sign that screams, hey, a redox reaction just happened here. So we know the players and we know how to keep score. But how do we write out the full chemical equation? Well, the trick is to break the reaction into 2 parts, the oxidation and the reduction, and balance them separately. We call them half equations. And for balancing these in an acidic solution, there's a fantastic step-by-step recipe. First, you balance the main elements. Then you use water molecules to balance out any oxygens. Then use hydrogen ions to balance the hydrogens you just added. And for the grand finale, you add electrons to make sure the charge is the same on both sides.
Let's use that recipe on another really colorful reaction. We're going to balance the half equation that shows the orange dichromate ion turning into the green chromium 3 ion.
So let's follow the steps. Step 1, balance the chromiums. Put it 2 on the right. Step 2, balance the 7 oxygens by adding 7 waters. Step 3, that adds 14 hydrogens, so we add 14 H+ ions to the left. Finally, we tally up the charge on both sides and add 6 electrons to the left to make them equal. Voila! The books are perfectly balanced. So you might be thinking, okay, that's a neat accounting trick, but why does it matter? Well, it matters a lot.
We can use all this knowledge as an incredibly powerful tool for analysis. Think of it as being a chemical detective, figuring out exactly how much of something is in a sample.
So here's our case. This bottle of iron supplements claims there are 200 milligrams of iron in every single tablet. Is that true? Or is the manufacturer pulling a fast one? How can we, as chemical detectives, find out for sure?
Absolutely. We can solve this with a technique called a redox titration. Here's the plan. We'll dissolve one of those tablets in acid, which releases the iron 2+ ions. Then, we'll slowly react it with our purple permanganate solution, which we've measured out very, very carefully. Now, as we add the permanganate drop by drop, it instantly reacts with the iron, and that deep purple color vanishes. Poof! But eventually, we'll reach a point where every last iron ion has reacted. And at that exact moment, the very next drop of purple we add has nothing to react with, so it stays, turning the whole solution a faint pink. That's our clue. That tells us the reaction is over. And from there, the detective work is pretty simple. We measure exactly how much of our purple solution we used to get that pink color. Then we look at our balanced equation, which tells us that for every 1 permanganate ion, 5 iron ions reacted. And from that ratio, it's just a bit of math to figure out the exact mass of iron that was in the tablet. So what did our investigation find? The lab results are in, and the tablet contains 199.8 milligrams of iron. The company's claim of 200 milligrams was right on the money. Case closed. So there you have it. From rust to respiration to detective work, it really is all about tracking the electron, the fundamental currency of chemistry. You now have the tools to follow that currency, to understand the rules of this great exchange. It's the key to unlocking so much of the world around us. So the only question left is, what chemical secrets will you uncover next?